Hi, my name is Ying. I'm a research fellow in Monash University in Australia. I'm going to present our work towards immersive collaborative sensemaking. This is the work with Dwyer, Wybrow, Benjamin Lee, who are also from Monash University, Maxime Cordeil from the University of Queensland, and Mark Billinghurst and Bruce Thomas from University of South Australia. And our work is about comparing collaborative sensemaking using desktop conferencing and virtual reality environment. Remote collaboration is more popular right now than ever before. Video conferencing tools such as Zoom are widely used for this matter. And when talking about collaborative sensemaking, which means working together to make sense of information, online shared whiteboards like Mirrorbot provide a platform to support presenting and managing information like documents, notes, or images for people to make sense together. Immersive environments provide three-dimensional space like physical world and give a strong sense of embodied presence, offering potential benefits on co-presence and group awareness in collaboration. And related work has investigated collaborative sensemaking on graph connectivity, data analytics, and document arrangement in VR or AR. However, little research has been done to directly investigate whether immersive environments can better support group sensemaking tasks compared to desktop environments. So that's why we decided to investigate. And we conducted user studies and developed measures on the collaboration to do the investigation. Here are the two conditions we set up for the user study. The desktop and VR systems used in the study were developed using Unity, and the functions of both systems were designed to have as close equivalent features as possible. The desktop condition is based on online collaborative tools like Miro, with communication handled via Zoom video calls. The system allows participants to move objects around the shared 2D canvas using their mouse. Like in Miro, participants could see the positions of others' mouse cursors on the canvas. And the VR condition used Oculus Quest 2 with controllers and allowed for the objects to be freely placed in the 3D place. Participants can see others as embodied avatars and can talk to one another using 3D spatial audio captured by the headset's internal microphone. And as sensemaking often involves arranging information in the working space, we therefore designed image organization tasks for the user study. The tasks required participants to arrange a set of images into groups around a set of effective labels, such as happy, sad, and calm. The participants were asked to discuss their feelings about the images and reach a consensus to place the images near the corresponding labels. We designed 4 tasks and varied the number of image groups and images for each task. The first task had a list group and fill its images. It was used to allow participants to get used to collaborating in the shared environment. And the number of images in other tasks was similar, with the number of groups increased gradually in the tasks. The images we used in the user study were from the Open Effective Standardized Image Set. It contains around 900 images. Each image has values on 2 dimensions, valence and arousal. And the emotion tones we used in the user study as group labels were selected from the affect model developed by Russell, which also organizes the tones in valence and arousal coordinates. So in this case, we combined these 2 datasets and matched the distribution of the images to the emotion tones as the ground truth for the image grouping. And when selecting these images for each task, we try to maximize the distance between the groups and minimize the distance between the images within a group. We recruited 10 groups of 4 participants, in total 40 participants for the user study, and it was a between subject study. In the study, each condition followed the same procedure, and after logging into the system, participants firstly did a training separately in individual virtual training rooms to learn the functions and interactions of the system. And after the training, participants joined a virtual meeting room before doing the real task. One experimenter also joined the meeting room to guide the participants. And in the meeting room, participants were asked to introduce themselves to others and then do an ice-breaking activity to share which animal they wanted to be if they could. Then the experimenter brought the participants to the task room to do the tasks. And in the task room, the images and labels were evenly distributed on the cameras in the desktop system or in the room on the waist height in VR. The procedure of the tasks were fully controlled by the experimenter. When participants finished one task, they needed to ask the experimenter to change to the next task for them. And after the study, participants were asked to complete questionnaires about their experience during the collaboration and also their demographic information. And for the data collection, we logged the positions of participants' images and labels, and also participants' actions during the study. We also recorded participants' voices. We provided systematic measures and developed new tools to analyze user behaviors and their collaborative experience. We analyzed groups' task performance in terms of accuracy and completion times, and explored participants' activities in terms of interaction, conversation, and coordination, and also engagement with respect to awareness and social presence. For task performance, we did not find significant differences on accuracy or completion time between 2 conditions. And for interaction, as can be seen from here, VR participants spend much longer time on interacting and organizing objects than desktop participants. And they also had much more interaction counts with objects than desktop participants. And the reason for this could be that aligning objects in 3D space requires more effort than in 2D space. We also analyzed the interaction equality between participants within groups in terms of interaction duration and interaction count. The only statistical significant difference is in grab duration. For the analysis on conversation, we can see VR got more verbal communications between participants than desktop. This could be attributed to that VR increased the sense of physically being together in the space and working with other people. Regarding coordination, desktop participants spent more time on monitoring others than VR participants and protected their own works more than in VR. This could be due to that it is harder to get an overview of the space in VR than desktop, especially to notice what is happening outside the own field of view in immersive environments. But however, participants in VR respected others' work more than in desktop. We suspect that the greater presence and awareness of working with others made the participants respect others more in VR. For awareness, we found that more no-response conversations happened in desktop than in VR. However, there were more conversation conflicts happened in VR than desktop. And we even found some interesting parallel conversation happening via regardless participants' distance. But we did not find significant differences on social presence rating between two conditions. Besides the quantitative analysis, we also analyzed the study visual replay from the logged data, and we identified some patterns of the image organizations in the two conditions. As can be seen from here, VR participants created more diverse organizations than desktop participants, although there are common patterns like the rows, columns, and clusters between the two conditions. And the most interesting organization here, I would say, is the 3D convex hall. So basically, the participants built a table in the center of the room for discussion. In summary, our results suggest many positive outcomes and potential advantages for collaborating sense-making VR over a more standard desktop environment. And for future work, we plan to explore other sense-making tasks for collaboration, like problem solving or brainstorming. And for communication, as we found, there were much more conversation conflicts in VR. We could possibly implement automatic sound adjustment in the system to focus on users' conversation targets. And regarding notification, which is related to the coordination findings, we consider to provide some functions to increase the ability for users to be aware of changes in the shared space in VR. And for spatial organization, from the interaction analysis, we can see there's a need for auto-alignment of objects to facilitate easy placement in VR. Also, as there were diverse patterns produced by participants, we could consider to have some smart automatic placement mechanisms to support diverse spatial organizations. And there were also many other possibilities for future works. So we believe group immersive sense making is a rich area for future research. And this is my presentation. Thank you.